Hi everybody, today we have an intro to solving trig equations. Because we have an intro, that means there'll be other videos with more complicated equations coming in the future. But for now, we want to start with how do we solve trig equations and what's important to know about them. So to solve trig equations, I want you to think about solving regular equations like 2x plus 3 equals 5. When we solve these types of equations, we get a singular solution. When we solve trig equations, like 2 times sine x plus 3 equals 5, the number of solutions is going to depend on the restrictions placed on the equation. When we look at trig equations, we want to find all solutions to the equation. Sometimes we'll be given a restricted domain, then we'll only have to find the solutions in that particular domain. So let's start with a restricted domain. I have 2 times the sine of x plus 3 equals 5, but we're only going to solve from 0 to 2 pi. I'll start by moving the 3, and I'll have 2 times the sine of x is equal to 2. I'll also divide by 2, which says the sine of x is equal to 1. To find x, I'll find the sine inverse of 1. If you think back to your unit circle, you know that sine is equal to 1 at pi over 2, so that means x will be equal to pi over 2. We don't have other solutions this time because we have a restricted domain of 0 to 2 pi. If I take away the restriction, I'm going to have a lot more answers. We're still solving the equation sine x is equal to 1. To help you visualize the solutions to this equation, I'm going to graph the left side as y equals 2 times the sine of x plus 3, and I'm going to graph the right side as y equals 5. The points of intersection will be the solutions to the equation. I notated our x equals pi over 2 that we had from solving the first time. But notice I also have a 5 pi over 2 as an intersection point. I have negative 3 pi over 2, and I have negative 7 pi over 2. The distance between the pi over 2 and 5 pi over 2 is 2 pi, which is the period for sine. That's the same distance that I have from pi over 2 to negative 3 pi over 2, and from negative 3 pi over 2 to negative 7 pi over 2. What this is showing me is that all of the solutions to the equation can be written as x is equal to pi over 2 plus 2 pi k, where k is an integer. That means k could be positive or negative, but we'll have infinitely many solutions to this equation when I don't restrict the domain. Let's solve the equation tan theta equals 1. We're going to give a general form for the solution, and then we'll list 6 solutions. Just like our last problem, we're going to start with tan theta equals 1 and find the inverse. So I say tan inverse of 1 is equal to theta. If you think about where a tangent is equal to 1, it would be at pi over 4 and also at 5 pi over 4. So I have these two angles to start with. I want you to notice tangent is positive in quadrants 1 and in quadrant 3. Also, tangent has a period of pi, so I can see that pi over 4 and 5 pi over 4 have the distance of pi apart. When I'm looking for my general solution, I'm going to say theta is equal to pi over 4 plus pi times k, where k is an integer. We're going to list 6 solutions. Well, we already have 2. We have pi over 4 and we have 5 pi over 4. When we're adding pi, to get more solutions, I'm going to think of pi as 4 pi over 4. That way I have a common denominator. 4 plus 5 is 9 pi over 4. I add 4 more, there's 13 pi over 4. I add 4 more, there's 17 pi over 4. And my last one would be 21 pi over 4. I could have also subtracted 4 pi over 4 and got negative solutions, but I decided to use all positive numbers. Next I have 2 minus the square root of 3 cosecant of theta equals 0. I'm looking for a general solution, and then I'm going to give 4 solutions. I'll start by moving the 2. I have negative the square root of 3 cosecant of theta equals negative 2. I'll divide by negative the square root of 3, which says cosecant of theta is 2 over the square root of 3. We can rewrite that as 2 times the square root of 3 over 3 if we want to rationalize the denominator. It may also help to think about cosecant as being 1 over sine of theta. That way, I can think about my unit circle and think about at what angle do I get the square root of 3 over 2. Square root of 3 over 2 would be up here at pi over 3. Sine of pi over 3 is the square root of 3 over 2, which says cosecant of pi over 3 is 2 over the square root of 3. Sine is positive in quadrants 1 and 2, so I know I also have an angle in quadrant 2, which would be 2 pi over 3. When I write my general form of the solutions, I think about theta being equal to pi over 3 plus 2 pi k and 2 pi over 3 plus 2 pi k. We're supposed to list 4 solutions. We already have 2. We have pi over 3 and we have 2 pi over 3. My period of 2 pi can be expressed as 6 pi over 3. So if I add 6 to pi over 3, I get 7 pi over 3. If I add 6 to my 2 pi, 6 plus 2 gives me 8 pi over 3. The next problem says solve the equation over the interval 0 less than or equal to theta less than 2 pi. I have 1 minus cosine theta is a half. I'm going to write that as negative cosine theta. A half minus 1 is negative 1 half. I'm going to cancel the negatives and I have cosine of theta equals 1 half. Now I need to find the cosine inverse of 1 half in order to find theta. Cosine is positive in both quadrant 1 and in quadrant 4. So I know I should have 2 solutions to start. In quadrant 1, cosine theta will be pi over 3. In quadrant 4, theta will be 5 pi over 3. Let's try 3 times the square root of 2 cosine theta plus 2 is negative 1. I'm going to first move the 2, which says I have 3 square root of 2 cosine theta equals negative 3. Then I'm going to divide both sides by 3 square root of 2. Now I have cosine theta. The 3's cancel. I have negative 1 over the square root of 2, which I can simplify to negative the square root of 2 over 2. Cosine is negative in quadrants 2 and quadrant 3. Cosine inverse of negative square root of 2 over 2 is going to give me 2 solutions. In quadrant 2, I'm going to have 3 pi over 4. And in quadrant 3, I'm going to have 5 pi over 4. Our final answer says theta is 3 pi over 4 and 5 pi over 4. We're going to solve 2 sine squared theta minus 1 is 0, where theta is from 0 to 2 pi. My first step is to move the 1. I have 2 sine squared theta equals 1. That says sine squared theta is equal to 1 half. I'll take the square root of both sides, which says sine theta is equal to. When I take the square root, I need to write plus or minus. Square root of 1 is 1. Then I have the square root of 2 on the bottom. I write this as plus or minus the square root of 2 over 2. Because I have the plus or minus, it means I'm going to have a solution for all 4 quadrants. The square root of 2 over 2 is going to go with odd multiples of pi over 4. That says theta will be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Next, we're going to solve sine of 3 theta is negative 1. This one's a bit different because we don't just have theta, we have 3 theta. So I really want you to pay attention to what's going to happen to our solution. I don't have anything to move around. All I need to do is say sine inverse of negative 1 is equal to 3 theta. Well, thinking back to our unit circle, we know that sine is negative 1 at 3 pi over 2. So I have that 3 theta is equal to 3 pi over 2. Because I have this 3 with my theta, I'm also going to put in the period of 2 pi k. Other solutions can come up because I have this coefficient of 3. To get to theta, I need to divide everything by 3. So I'll divide 3 pi over 2 by 3, and then I will divide 2 pi k by 3. This says theta is equal to pi over 2 plus 2 pi over 3 times k. We need to find all the values of theta that are between 0 and 2 pi. I'll start by letting k equal to 0. I'll get theta is just pi over 2. 0 times 2 pi over 3 will go away. If I let k be 1, I'll have theta is pi over 2 plus 2 pi over 3. I need a common denominator, which would be 6. 3 pi over 2 will become 3 pi over 6. 2 pi over 3 will become 4 pi over 6. 3 plus 4 gives me 7 pi over 6, which is between 0 and 2 pi. Let's try k equal to 2. I have theta is pi over 2 plus 2 times 2 is 4 pi over 3. I'm going to use the same common denominator of 6. We know pi over 2 is 3 pi over 6. 4 pi over 3 will become 8 pi over 6. When I add 3 plus 8, I get 11 pi over 6. When I add 3 plus 8, I get 11 pi over 6. I'm not going to put in the next number of 3 because I know I'm already so close to 2 pi that I'm not going to get another value. So my three answers are pi over 2, 7 pi over 6, and 11 pi over 6. Our last couple problems involve using a calculator. We're given that the cosine of theta is 0.6 and we want to find all solutions from 0 to 2 pi. We'll round our answers to 2 decimal places. I'll start by saying cosine inverse of 0.6 is theta. When I use the calculator, I need to make sure that I'm in radians. I'll do cosine inverse of 0.6, which is 0.927, which I'm going to write as 0.93. Cosine is positive in both quadrant 1 and in quadrant 4. The 0.93 is our answer in quadrant 1. To get our answer in quadrant 4, I need to take the cosine inverse and subtract it from 2 pi. 2 pi minus 0.93, which is 5.35. Our last problem says 5 tangent of theta is negative 9. I'll start by writing tangent of theta is negative 9 over 5. Then I want to take the tan inverse of negative 9 over 5, and that's going to give me theta. Tangent is negative in quadrants 2 and in quadrants 4, so I expect 2 solutions to this problem. To get my first solution, I do tan inverse of negative 9 divided by 5, which says negative 1.06. The negative puts the answer in the fourth quadrant. To get my second solution, I'm going to add pi, which is the period of tangent. This gives me theta is 2.08.